All right, welcome back, class. We're just picking up where we left off with forest economics. All right, so we talked a little bit about rotation age and having this optimal rotation age. And so, why even bother about all this, right? Your goals may change, markets fluctuate. Why even care about this? Because you may have non-timber objectives, right? And is it even feasible? Regulations or guidelines might change, forcing harvest at a different point, right? And so it doesn't really always make sense to have this optimal rotation age if we're kind of taking it from an abstract point of view, right? You may not always be able to harvest these trees when you're saying you should be, right? So why even do it? Well, this estimate of an optimal rotation age provides a framework for our management activities, right? Throughout from early tending, right? That site prep, all the way through our intermediate treatments and that final harvest, right? And this allows us to see if our stand is on target. Do we need more intermediate treatments, right? Should we be doing PCT? Is this regeneration successful, right? We need this rotation age for planning, right? And of course, this is from an even age management perspective, right? But if you never have your end goal, how are you going to end up there, right? If you're just like, we'll just let it happen, we'll just let it grow on its own. If you never define your objective, right? How will you obtain that? So having this optimal rotation age provides us an endpoint for our stand, where we are trying to get to and when. So as you might recall, there's two objectives that we commonly look at here: maximizing volume production or maximizing profit and or minimizing our costs. So there's kind of two new terms I'm going to be introducing to associate with these two different objectives. So wood volume production would be a biologically optimal rotation age, while this maximizing of profit in our net present value, right, would be a financially optimal rotation age. And so let's look at this again. And so we can also think of biological optimal rotation age as the ecological rotation. And so this is where we are performing our rotation age based on biology. When is the stand volume going to maximize? When will that growth rate decline, right? And what we're looking for is that culmination of MAI. When is our mean annual increment peaking and then declining? We want to harvest it at that peak, right? This maximizes the total stand volume. As you recall, a younger forest will put on more carbon. It sequesters carbon more quickly. At a certain point, an older forest will start to taper off, right? The periodic annual increment, how much it's growing on a yearly basis, can be decreasing, but we want to see that mean change. The mean will lag behind. On the other hand, we have an economic rotation, right? This is our financially optimal rotation age. And this takes into account the discount rates or interest rates or your return on investments to maximize your net returns. Generally speaking, the higher the discount rate, the shorter the optimal rotation age. Furthermore, in general, we'll often see that the economic rotation age is generally shorter than the ecological rotation age. Not always, but often so, because we have to carry those costs of investment further and further into the future, right? Decreasing the value of that return in the future due to inflation. And so let's dive more into this biologically optimal rotation age. You guys might remember this from lecture on Tuesday, right? So this maximizes stand volume. And so stands with a higher site class, right, a higher site index, will reach this culmination of mean annual increment sooner. So it's just something good to know there, right? Those trees are going to be growing more quickly, and that decline in productivity will also occur sooner, right? Because you'll see these trees get older and they're not growing as quickly anymore. So they're not able to take advantage of that higher site class to the same degree anymore, right? Again, MAI, that's our mean annual increment. That's the average amount grown over the whole life of the stand. This is merely the total yield divided by the total age. We are going to harvest under the ecological rotation age or biologically optimal rotation age at the peak of MAI. This is known as the culmination of MAI. If you look at the graph here, you can see our average annual growth. In this case, it's the mean annual increment is what that's referring to. And then the annual growth. That's your periodic annual increment. How much does it grow each year? Then the annual growth, this orange line, that's your mean annual increment. That's the average growth over time. And so what we first see is your periodic annual increment, PAI, or in this case, annual growth, will peak and it starts to decline. The mean lags behind this. And at one point, they will intersect. Where these two intersect is where your mean annual increment will start to decline. At this point, mean annual increment has peaked, and this is where you should be harvesting under a biologically optimal rotation age. And so a little bit about our volume terminology, right? We're trying to maximize our volume. So often here in the US, we use board foot or board feet, right? And this is a piece of wood that's 1 foot by 1 foot by 1 inch, or 12 inches by 12 inches by 1 inch. It has a cubic volume of 144 cubic inches, right? And so in your standard 8-foot long 2x4, it's about 5.3 board feet. And mind you, that's before they dry it and they actually dress it down a bit more and plane it, right? It actually becomes a 1.5 by 3.5. But rough sawn timber, a rough sawn 2x4 that's 8 feet long will have 5.3 board feet approximately, right? You'll also see these other terms that just expand on board foot. MBF, either all capitals or all lowercase, will be 1,000 board feet. It's just shorthand for that. You also see capital M, then lowercase bf, or MMBF, and that's for million board feet, right? It just saves you some time, sometimes make these numbers easier to read. You also see cubic volumes sometimes used. These can be centimeters cubed, meters cubed, inches cubed, or feet cubed. And so you'll often see that more in research papers or abroad. And so how many board feet would be in a cubic foot? Well, you can take 12 inches times 12 inches by 12 inches, right? A foot times a foot times a foot. And that gives us 1,728 inches, right? And then you can divide that by 144, which, as you see, I did not do here. And so let's just do that real quickly. I made a mistake in these slides. It's always something, right? But 1,728 divided by 144 cubic inches gives us 12 board feet, right? So I just had those numbers flipped in my rush to get everything done. And so always check your work, everyone, even your lecturer needs to. So 1728 divided by 144 cubic inches gives us 12 board feet. And here we can see two different images, a 12 by 12 by 1 and a 12 by 6 by 2. These both represent 1 board foot. Okay, wonderful. And that wraps up volume terminology. Let's go on to financially optimal rotation age. Talked a little bit about this in class on Tuesday, right? So this is where you're trying to maximize the present value, right? And this present value maximization is what drives our management decisions. Frankly, this is what we generally see, right? We are in a capitalist economy. It's all about the money, sadly. So, though we should be valuing these other objectives, right? Not just our economic incentives, right? There's ecological incentives as well. But without a dollar amount assigned to those, how can we put those into an understanding of our management decisions, right? How do you put a value on things that might be inherently infinite in their value, right? So I think it's good to try to put a number to some of those ecosystem services that our forest might provide, that we can take this into account, right? And so the standard discount rate used for our forest economics is generally in the 4 to 6% range. And so you can use that for your estimate of your net primary value, where your future value minus your current value and all that good stuff, right? Check that equation though. And so again, the issue is once you have higher and higher inflation rates or higher and higher discount rates, you need to have a faster growing stand to exceed this discount rate. Otherwise, you'll want to harvest it sooner to maximize your economic return. If inflation is occurring more quickly than your stand is growing, you're losing money by delaying harvest. So isn't that a trip? And so in this way, you could use percent basal area. And so if the percent basal area of this growth does not exceed this discount rate, you will need a harvest, right? Basal area, our cross-sectional area represented by our trees in the stand at breast height, right? That two-dimensional space. Here's a review of the equation. There should be a horizontal line there. So it's future value over 1 plus I to the nth power, where n is the number of years and then I is the rate of return. Often we use 0.04 to 0.06, right? Future value divided by 1 plus I to the n. And so looking at this again, we can see that there's a bit of a rise, right? There will be a point where this discount rate may be exceeding the growth rate. So we're seeing the growth rate exceeding the discount rate. Now our growth rate's declining in a way, and we're seeing this present value being impacted by this discount rate. So once again, your growth will need to exceed this discount rate. Otherwise, it will make sense to harvest it sooner, right? In general, the higher the discount rate, the shorter the rotation age. Not always, but often so. All right, just a quick little short lecture just to get you guys a little more thinking about all this. I know it wasn't perfect, but guess what? We aren't always going to be perfect. And I'm glad for you guys to attend this virtually, your first recorded lecture. And so let me know if you have any questions. I know this is quick. We will work over some net primary value problems in class come Tuesday. Reminders on Tuesday and Thursday, we'll have a lab in our 223. We'll go over some equipment safety. I'll bring some equipment to the lab and we'll just talk about PPE maintenance and what you should be doing and what you should not be doing. Let me know if you have any questions. Feel free to shoot me an email and all that good stuff. No homework due Tuesday, but work on that stand density in the ACF lab, right? That's due next Friday after our exam, right? You should be studying exam 2 Thursday of next week. All right, be ready. See y'all then.